Welcome to this video. In this video, we will start talking about machine learning. To introduce the topic, we can understand machine learning as a new programming paradigm. In the classical programming paradigm, the programmer has data and also has rules that represent the business logic to process this data. The purpose of the programming task itself, the development of the computer program, is to convert data to answers using the rules. For example, let's think about a tax preparation software. The data itself is the data about the tax applicants, information like demographics and salaries, things like that, as well as the tax code itself that corresponds to the rules applied to the data to get the answers, which is the tax liability of the users of the software. The machine learning paradigm is different because we don't have rules, rather we have a large amount of data and answers. And the purpose of the machine learning program is to uncover the rules that map data to answers so that we can use it for future data that we don't have answers to yet. A classical example, for instance, is spam detection. In this example, we have a large amount of emails classified as spams. Now, there are no rules that map a certain email to a spam, and that's the purpose of the machine learning algorithm. The classifier in this example is to create the rules that allows us to classify future emails as spam or not spam. We're going to do this simple exercise. We're going to start with a classical programming paradigm by writing a program to implement this decision tree. And then we're going to write a machine learning program to basically uncover this decision tree from the data provided us by this program. And this decision tree is basically a loan application approval program. Depending on information such as income, criminal record, years in present job, as well as making credit payment on time, the loan applicant is either approved or not approved to get a loan. This is a classic example of a decision tree, and presumably some decision makers in the organization have come to create this decision tree based on their experience. And this decision tree encodes the business rules. This function here implements the decision tree in a series of if-else statements to basically process the input, the data, which is the income, the criminal record, years in job, and credit payment, to eventually return a result which is either 1 or 0 for loan or no loan. Obviously, once this program is created, we can use the program to get answers to new data, for instance. So for instance, based on the income, the criminal record, years in job, credit payment, I can get a result of whether the loan is approved or not. The next step is to basically forget that we have such a decision tree. I'm going to forget that we have rules. Instead, I'm going to simulate creating a lot of answers for many data points and try to uncover the rules again using machine learning. So what I'm going to do here, I'm going to simulate a lot of numbers, many incomes, criminal record histories, year in job, credit payment, and also make a decision. So in the example here, we simulated 100 hypothetical loan applicants, and the data is collected in this data frame. Now in real life, this data can be found about, for instance, by tracing the decisions that expert loan officers are making over time, and then we try to estimate a machine learning model so that we can apply the model on new data. And this is what we're doing here. We're going to talk about decision trees in more details in the coming sessions, but decision trees are one model that can be estimated using existing data. The basic idea here is that as machine learning designers, we select the model that we want to fit using the data. So we supply the model the data we have on hand, and this is called the training data. This example of training is what we call supervised training because we have the input, which is the income, criminal record, years in job, credit payment, as well as the desired output, which is the decision on the loan application. Once we fit the model itself can be used for both making decisions, predicting decisions, outcomes for new values, as well as understanding the process that led to that decision, what we call for explaining the decision process inherent in the data. If we take a look at the decision tree, what I have done here, I printed the decision tree and it shows up in a kind of textual format. And as you can see here, the decision tree at each level of analysis is looking at one variable. For instance, it's looking at income. And if income is less than 16,421, it's going to look at the criminal record. If it's less than 50%, which means it's 0, it's going to deny the loan. But if it's more than 0.5, it's going to approve the loan. If you take a look at the decision tree here, it's kind of picking up this branch, except that the values here are not exactly the same. So basically, for low income applicants, if they have a criminal record, they're giving a loan. If they don't have a criminal record, they're not giving a loan. So maybe the decision tree doesn't make sense. It's for illustration purposes, but you can see that the decision tree has kind of uncovered this branch of the tree. We can go through the remaining steps in the decision tree. If income is not less than 16,421, it's going to look at another kind of cutting point, which is 70,000, and it's going to make further decisions based on the other variables. So once again, it doesn't match exactly, but you can see that here it's kind of picking some of the information that we have on the branching decisions. And in none of these data points we have exactly that numbers. This whole decision tree is induced from the data, is learned from the data. And the data here is very sparse. Actually, you only have 100 observation. And this decision tree is not the most optimized decision tree. We will learn more about how we can optimize the decision trees furthermore. But that kind of serves to kind of illustrate the concept. Even with little data, with a very kind of primitive model, one can come up and create a model that kind of uncovers hidden patterns in the data. That's basically the idea of machine learning. We're going to talk more about some of the concepts that we're going to discuss in more details in the next lectures. So machine learning in general, it's kind of estimating or building mathematical models to help understand the data as well as predicting outcomes for new data that we don't have. There are two generic categories of machine learning: supervised learning, and in this case we have models that can predict labels that we have in label training data. The example of the loan application is an example of a supervised learning. And depending on what we're predicting, there are two kinds of supervised learning applications. Classifications, when we are predicting labels that are discrete categories. Again, the loan application is an example of classification here because the decision, the outcome is either loan or no loan. And regression, when the outcome is continuous. And supervised learning, on the other hand, are models that identify structure in the unlabeled data. So we don't have a label of a certain outcome that we want to predict, but we want to uncover some inherent relationships in the data. There are two broad applications: clustering, which is detecting clusters or groups in the data. The example we looked at when we did network analytics last week is an example of clustering, where we had purchasing data that we managed to group in 3 different or 4 different clusters of books. Dimensionality reduction is basically trying to reduce and compress the high dimensions of a data to a lower dimension that keeps most information about the data. We're going to illustrate this concept with some kind of visual examples. Let's take a look at classifications. Let's say we have two variables, and those variables in the lingo of machine learning are called the features. And we have a bunch of observations. So each observation is a combination of the two features, and the color is basically the output, the outcome that we want to classify, to predict. So the idea of a classifier is that we want to have a model that distinguishes between this group, class blue, and this group, which is class red. One classifier, for instance, can be a line that separates these data to two groups. On the other hand, let's say we don't have a categorized outcome. Let's say the outcome is continuous. And in this case, we want to predict the outcome. You can see that the color of these dots is now a shade from yellow to dark blue in this case. If we want to predict the intensity of the color, that's an example of regression. In this data, we have two features, feature 1 and feature 2. So we can actually think about the outcome, the color of the dot, as a third dimension, because this can be also a continuous number from light to dark, for instance, and the third dimension can help us visualize this data as a three-dimensional data set. In this example, you can think about the task of learning the color, which is the regression task, as basically trying to fit some surface area, such as a plane in the space, that matches or kind of fit or sits on top of these points in the three-dimensional space. If the surface area is linear, we have an example of what we call a linear regression. Clustering, on the other hand, is an example of unsupervised learning. We don't have a color that distinguishes the class, the category, or the outcome of these different dots. But even looking at these dots, they have two features here, we can immediately uncover that there are different group structure. And clustering is an example of an algorithm that uncovers this group structure in the data. Of course, this data set is for illustration purposes, and it's easy for us, if we have two features, to use our visual perception system to uncover this group. Once we have a high dimension, like for instance, instead of two features, let's say we have 200 features, it becomes hard to detect such groups. So an example of clustering is basically to associate each one of these observations with a corresponding group. In the next lecture, we will see detailed examples of each one of these machine learning techniques.